Hey guys, welcome to AI Tech Talks with Carl. In this video, we are going to go over a decision tree classifier with weighted samples and the formulas that are used in the tree growing process. The end goal of this tech talk is to be able to calculate the weighted impurity decrease we get from splitting a decision node. We start off with a general decision tree and a training example X with two predictors of X1 and X2. The thresholds used for this decision tree are given as T1, T2, T3, and T4. In this decision tree, the terminal regions are indexed with R, and the decision nodes are displayed in blue, with the left child as the observation following the expression and the right child as the observation not following the logical expression. Now, this binary tree with terminal regions and split points can be represented in a different format as a 2D graph. In this 2D spatial representation of the decision tree, the first predictor or feature is on the horizontal axis and the second predictor is on the vertical axis. We start out at the root node, which splits the first predictor less than or equal to T1. Then, if the second predictor is less than or equal to T2, the observation will go to R1, and if greater than T2, it will go to R2. Thus, the binary tree is represented in a 2D spatial coordinate system with the regions as labeled rectangles. The same thing can be done with the right child of the root node, where the first predictor is split at threshold T1. Now we can define our training examples within our spatial representation and label each example as either class 0 or class 1 for a binary classification problem. Thus, for each example here, we have a class of 0 or 1 and a sample weight attached to each example. Algorithms like AdaBoost require the sample weights to be normalized, so I defined a decision tree with the sum of all the weights equal to 1. We can then define a simple threshold as a candidate split, with a threshold of T1 to split the data set with the first predictor. This is essentially equal to a stump with the root node as a logical expression of X1 less than or equal to T1. Now, how do we see if this is a good candidate split for this decision stump? Our goal in this video will be to find the weighted impurity decrease for this example. Let's move this up a bit and define the different impurity measures used for decision tree classification. These impurity measures are the Gini index, which is the sum of P times 1 minus P for all classes, and cross entropy, the negative sum of P times log of P for all classes. The P is the proportions of classes in the node, also called the probability of a class inside that node. We will be going over the Gini index for this example because it is the most popular measure used for tree growing. We can expand the sums for each class in the example and get the following equations. The Gini index for the parent uses all of the observations in the current node that we are trying to split. Let's start with the parent node. The proportion of examples of class 0 in this node is the sum of all the weights associated with that class divided by the sum of weights for observations of all classes. Since the weights are normalized for the decision tree, the sum of all the weights is just equal to 1, and the probability is 0.5. The probability of class 1 is the sum of all the weights for class 1 divided by the sum of all the weights again. We get 0.5 again for the probability of class 1, and then all we need to do is plug and chug into the formula for the Gini index. After computing the sum, we get 0.5 for the Gini index of the parent. Moving to the Gini index of the left child, we can use the same equation from before, but only use the samples in the left child. The probability of class 0 is calculated as the sum of the sample weights of class 0 over the sum of all sample weights in the node. The probability is then equal to 0.2 for class 0. We then divide the sum of the sample weights for the first class over 0.5 and get 0.8 for the probability of class 1. We can plug those probabilities into the formula for the Gini index and get 0.32 as the Gini index of the left child. The Gini index of the right child is calculated in the same way as the left child, and we end up getting the same value of 0.32. This means that the impurity measure is the same value for the right and left children of the root node. All that's left to do now is to calculate the weighted impurity decrease to see how good the candidate split was. The formula for weighted impurity decrease is the number of samples in the parent node over the total number of samples. This quantity is multiplied by the parent impurity minus the weighted right and left impurity. We can use our calculated Gini index as the impurity measure, while NR and NL are the sum of the sample weights in the right and left child nodes. Since our decision tree is only a stump with 2 leaf nodes, the number of samples for the parent node and the total number of samples are both equal to 1. Now let's plug and chug the values into the formula for weighted impurity decrease. The final value we get for the impurity decrease of this candidate split is 0.18. So in this video, we went over how to represent binary decision trees with 2 predictors as a 2D spatial representation. We calculated the Gini index of each the parent, left child, and right child nodes with the weighted probabilities, and used the expression for weighted impurity decrease to see if a candidate split was a good threshold to split the data. So that's it for this tech talk, guys. If you liked the video, please support the channel by subscribing and sharing with your friends.